We'll now take a look at another example of solving an ODE using substitution, and these are going to be Bernoulli's equations. A differential equation of the form dy dx plus p of xy is equal to f of x times y to some power, where n is any real number, is called Bernoulli's equation. We notice that we've seen kind of variants of this before. For n equals to 0 and also n equals to 1, the above differential equation would actually be a linear one. Okay. It turns out that this can be solved via the substitution u equals y minus 1 to the n reduces the equation of the form 4 into a linear equation. So essentially what you see here is we have almost, it looks like a linear, first order linear differential equation on the left hand side, but we have is some function f of x times some y to a power n. We want to let u be y to the 1 minus that power right there. And they claim that this reduces this to a linear equation, a linear differential equation under that substitution. Let me actually show you that that's the case. So let's actually go ahead and verify that. So let's let u equal y to the 1 minus n. And now let's go ahead then and compute the derivative with respect to x of both sides. So if we do du dx, this would be equal to the derivative of y raised to the 1 minus n. This would be, bring the power down. This would be y to the y 1 minus n minus 1. And then from the chain rule, or if you can think of it implicitly, the derivative of y with respect to x would be dy dx. Here the ones cancel, and so what we get is that du dx is equal to 1 minus n times y to the negative n dy dx. And we can take and we can solve this. Let's solve this for dy dx. I could simply divide both sides by this term, and what we would have, you end up with the algebra, you'll have a y to the n on the left hand side, 1 minus n du dx would be equal to dy dx. And now let's substitute these into this original differential equation. So everywhere we see dy dx, we're gonna put this expression. So we have y to the n divided by some factor 1 minus n du dx plus we have p of x y equals f of x times y to the n. And now let's go ahead and let's clear off the coefficient. So we want this to be a coefficient of 1 in front. So I'm going to multiply every single term by the reciprocal of this. So let's multiply by 1 minus n over y to the n to all of these terms. And of particular note, one of the things that we'll see is, first of all, this complete coefficient is going to cancel here. So that will leave us with du, color change issues. There we go. That'll leave us with du dx plus, now let's kind of inspect what we have here. We have 1 minus n times p of x. And now, I know my writing's a little bit sloppy, but that's supposed to be y to the n. This is y to the first. If you had y to the first divided by y to the n, that would be y to the 1 minus n. Equals to, on the right hand side, these cancel, and we get 1 minus n f of x. So we have du dx plus, this is just some coefficient times p of x. So I'm just going to rename that Let me just call it p twiddle of x. It's just some function of x. And notice, what is this? Y to the 1 minus n. Oh, that's just u. Equals to, and then likewise here, again, we're seeing this again, it's another constant times f of x. Then we call that f twiddle of x. And so, as was mentioned, this now is a linear first order ODE in the variable u. And we know how to solve this thing. We have our integrating factor. In this case, it would be what we're calling e to the p twiddle of p of x dx. So they were correct. They don't show it explicitly in the textbook, but now you can see it here. That it is true that if you have one of these Bernoulli equations, using the substitution u equals y to the 1 minus n, we'll convert it into a first order linear ODE, and then that's something we already know how to solve using our integrating factor methods. Okay? So let's do an example of one of these. In the book, I believe this is example 2. Let's solve x dy dx plus y equals x squared y squared. First things first, we would like to clear off this coefficient of x, so we want to kind of get rid of that. So this would be dy dx plus, I can write it as x to the negative first y here, nothing wrong with that, equals, we have x y squared. So we look at this and we say, okay, we have some function of x times y is equal to, on the right hand side, some function of x times y to some power. Okay, it's very important that with the linear, we want this y coefficient to be 1. And then coming over here, we see that this is a Bernoulli equation with n equals to 2. Okay, so recall that that substitution, when n equals to 2, the u sub that we make is we're going to let y be u equal y to the 1 minus n. So this is going to be y to the 1 minus 2, which would be y to the negative first power. So let u equal y to the negative first power. If we wanted to, we're perfectly able to get the y by itself. So this is the same thing as u equals 1 over y. Do the reciprocal of both sides, and we get that y equals 1 over u, or u to the negative first power. Let's take the derivative of this with respect to x. So dy dx is going to be equal to, we have a negative u to the negative second power, and then from the chain rule we have a du dx. Let's go ahead and substitute this into our differential equation. Everywhere we see dy dx, we can put our negative u to the negative second du dx. We have a plus x to the negative first. Everywhere we see a y, we can put u to the negative 1. And this is going to be equal to x times y squared. Remember, y is u to the negative first, so this is u to the negative first squared. Let's clean this up a bit. So we have negative u to the negative second du dx plus, and I don't know, maybe, I'm not sure if all of these negative exponents will drive you all crazy or not. Maybe I'll do some reciprocals. Change it up a little bit. So here's what we're looking at. This is essentially 1 over u squared du dx plus this is a 1 over x 1 over u equals x times 1 over u squared. And as we've seen before, we want to get this to be a coefficient of 1. we can get that to be a coefficient of 1 if we multiply every single term by negative u squared. What does that give us? Well, here these cancel, so we get du dx. This is going to give us a minus sign here. We have our 1 over x, and then u squared over u will give us u, equals, on the right hand side these cancel, and we get negative x. And indeed, this is going to be a first order linear ODE in the variable u. We can solve this with an integrating factor. So let's go ahead and do that. So our integrating factor is going to be e to the integral of p of x, where again this thing here is the p of x. So p of x is this. So it's e to the integral of negative 1 over x dx. Pull the negative out. Constant multiple rule. That is going to be the natural log of the absolute value of x when we integrate it. We can bring the negative up into the exponent as the absolute value of x to the negative first. And then the e and the ln cancel. So we get x to the negative first in absolute value. If we take this solution to be defined on 0 to infinity, which we're going to do on this one, then actually we can kind of drop the absolute value. And we're just going to look at this as x to the negative first. So if x is positive, we don't need the absolute value bars. We just get x to the negative first. Okay. That should turn this, if we multiply everything now by x to the negative first, this is going to turn this into an exact differential. So here's what we would get. So we would have d dx, remember it's always the integrating factor times u, would be equal to, now on the right hand side we would have negative x times that integrating factor, and that would simply be equal to negative 1. We could integrate both sides dx. Make some room. That's going to give us x to the negative first u equals negative x plus c. We can get the u by itself. To get the u by itself, let's multiply both sides by x. We get u equals negative x squared plus cx. And remember, if we go back to our substitution, what was u equal to? Well, u was equal to y to the negative first, or we had that y was equal to 1 over u. So our solution to this differential equation would be y equals 1 divided by negative x squared plus cx. And again, we were able to do that with a substitution. We recognize the equation as a Bernoulli equation. Just to kind of recap, those are of the form dy dx, plus we had some function of x times y is equal to some function of x times y to the n power. That makes it Bernoulli of order n. And then the substitution we want to do is let u equal y to the 1 minus n power. And as we saw, that turns it into a linear ODE, and then you can use our techniques of our integrating factor to solve it from there. Hopefully you're able to get the u by itself, so you can solve for u, and then we can back substitute to get our solution in the y variable.